Um, okay, maybe let's get started. So it's really a great pleasure to introduce Vincenzo Vitelli for our physics club speaker today. So Vincenzo got his PhD from Harvard, working with David Nelson on two-dimensional crystals and how they work on curved surfaces. He did a postdoc with Randall Kamian and Andrea Liu at Penn, and then moved to Leiden for a faculty job before moving back to UChicago, where he's now a professor in the physics department. Recently, Vincenzo has been doing a lot of really fascinating work on understanding topological modes in active materials and metamaterials, and as some examples, the edge modes in lattices of gyroscopes and fluids of active particles. And the work we're going to hear about today is about building a framework to understand phase transitions in systems where the microscopic interactions are inherently out of equilibrium. So very exciting work. With that, I'll turn it over to Vincenzo.
Hello. Hi, and thanks a lot. I would like to thank you very much for the opportunity to speak. I apologize for not being present there in person. And so I would like to tell you about non-reciprocal responses and phase transition. So my talk will have two parts. And I thought it could be a good idea to start by saying what we mean by non-reciprocity. And here is a pictorial first introduction to the concept. We will become more specific momentarily. So we have here on the first slides, you can see a red and the blue gyroscopes. The red one is labeled by B, the blue is labeled by A. The thing that we're going to demand is that the way the red interacts with the blue is different from the way the blue interacts with the red. And so this non-mutuality, this non-mutual or non-reciprocal interaction is the fundamental building block that will be interesting for us. And the motivation for studying systems that have this property, while much of our analysis will also, of course, cover physics problems, it's also very heavily motivated by context outside of physics. For example, if you study dynamical system that describes a network of neurons, often you have inhibitory and excitatory neurons that obviously have different effects on each other. Or in system with predators and prey, you don't even need to mention non-reciprocity of interaction is a natural ingredient built in. Now, what I would like to convince you that from a physics perspective, what will be interesting in our discussion is that the non-reciprocity we are focusing is characterized by the following property. The dynamics of these systems will generically be non-conservative in the sense that because of this non-mutual interaction, the dynamics will not follow from an optimization principle. So the usual passion that we as physicists have for going down the energy landscape, minimizing energy, will not be the right language to describe the systems. And as a preview of how this talk will be organized, I would like to say that, yes, we will be interested in what happens when you have many bodies, many such metronomes coupled, metronome or something else coupled non-reciprocally. And the talk is split in two parts. First, I will address response functions, how this many-body system respond to perturbation, using mechanics as active mechanics as an example. And then we will cover phase transitions in the second part. So first of all, let me say that by providing you a list that is by no means meant to be exhaustive, that these ideas on non-reciprocity, in the sense that I will discuss today, appear ubiquitously in many domains of science. For example, I just mentioned that in ecological studies of predator-prey systems, there is this inherent asymmetry. But also if you just study particles in a fluid and the fluid is an active one, or you drive the particle, tendentially the way they will interact will depend who is ahead and in front and who is in the back, as you can see pictorially here. Interestingly, and I'll expand also much more towards the end of the talk, many systems or coupled lasers or open quantum systems that are characterized by the simultaneous presence of gain and loss fall squarely in this category system in terms of mathematical description. And perhaps a bit more surprising even mechanical system, elasticity, which seems like the quintessential examples of a theory where the game is to minimize an energy. If you extend it to active systems, the internal sources of energy requires incorporating this notion. And I will tell you a little bit about what we call odd elasticity. So as I mentioned, let's start first with responses of non-reciprocal system. And to make that discussion very concrete, I would like to start with a recent work that we did in collaboration with experimentalists in the Cooley lab at Amsterdam, including Martin and Jonas, as well as my PhD student, Colin Scheibner. So let me give you a little example here. So what you see here is a little device created in the Cooley lab that is a nice, neat example of what I would call a non-reciprocal building block. And I would like to tell you in what way this device differs from, say, two coupled pendula with angular degrees of freedom that I very schematically shown here in the bottom of the slides. Now, in a system of coupled pendula, in fact, even uncoupled pendulum labeled by 1 and 2, the gist is that you will have an angular displacement corresponding to a torque. And if you displace either of them, there will be a restoring torque, which has an elastic or macroscopic coefficient kappa. Now, what the experimentalists in the Cooley lab did was to introduce, and you'll see why that is needed, some electronic feedback such that the angular degree of freedom, θ1 and θ2, so if you like, this angle here and this angle here, are now coupled by this asymmetric coupling. Notice that there's minus sign here and a plus sign here. So this is different in a subtle way that I'm going to show you from coupling with a spring stretching between the two ends, these two pendula. And this is particularly evident if you look at what happens when you touch the left hand, as one of my collaborators is doing, versus what happens when you touch the right hand, which is what you're going to see now. Okay. Now, this relationship that I show on the right that parameterizes mathematically this behavior is, if you like, a relationship between generalized forces, the torques, and generalized displacement. And when written in matrix form, you can see that the off-diagonal terms have an opposite sign. Whenever you have a construct like this force law cannot be written as a gradient of a potential, which is function of the angles θ1 and θ2 only. This force is inherently non-conservative. And that's why this experimentalist had to put batteries as well as feedbacks in there, as opposed to just connecting these two rods with a spring. And to summarize this non-reciprocal response, you can sort of see it on this slide. If you push on the left, the right beam comes in, okay, with respect to the unperturbed configuration. If you press the right beam, the left one moves outwards. So the asymmetry between these two responses is what you could call a non-reciprocity between what is on the left and what is on the right. And the crucial point that I want to stress is this point here. If the red terms are present in this microscopic torque versus displacement, angular displacement laws, then this torque, so this generalized forces, cannot be expressed as a gradient of a potential. The forces are, in a single word, non-conservative, okay? And one of the things that we want to understand is that if you take building blocks like this, that being non-conservative are able to inject or take away energy, and you construct now lattices of them, here is the many-body aspect that comes in, either one-dimensional chains wrapped up in a single circle, like here on the left, or the last lattice that you see here, this triangular lattice on the right, and you then subject them to perturbation, like throwing that bullet against a rigid wall or throwing a rigid object against this wall, you see mechanical responses that look strange. In particular, on the right here, you can see a chiral response. Even if the object is being dropped straight down, it recoils at an angle. And so one question that you can ask is that if you start with these microscopic building blocks capable of injecting or taking away energy, and you start rethinking elasticity, how would that look like? I mean, would it be the standard Cauchy elasticity that you learn in textbooks? And so to answer that question, let's remind ourselves that the textbook example of a building block for ordinary elasticity is springs satisfying some form of Hooke's law. So these are inherently conservative forces. That means that if you take this system around a loop in the space of displacement, you return to where it started, no work is done. But if you give up on that notion that the forces have to be conservative at the microscopic level, then work can be generated or absorbed depending whether you go on loops clockwise or counterclockwise. So if your building blocks have this property, maybe because they're connected to a motor, maybe because they're really building blocks of a biological system, then even at the continuum level, at the level of writing down a field theory that describes the coarse-grained system made of such building blocks, what you can have is you can take a system, a patch of your system, like this square here. You can deform it, for example, apply a cycle of shears. And when your media returns to its initial state, you will have done a cycle of deformations that even when are quasi-static, can extract energy or absorb energy. And one of the questions is, we want to understand how to describe the continuum mechanics, the elasticity of such a medium, okay? Now, if elasticity is not a new subject. I mean, this is a very well-studied textbook, the one where I first studied about it. So let's remind ourselves, how is elasticity, which is actually quite a complicated theory with its tensorial character, is usually presented. So I apologize if the next 2 or 3 slides are a little bit pedantic on insisting about indices, etc., but you'll see there is a reason for that. So often the way linear elasticity, which is the simplest form of elasticity, is introduced is via an energy function or an energy density denoted by F. And this energy density is a quadratic form of a strain field, this Uij, which is gradient in the j direction or displacement field in the I direction. And this horrible object, this Kijmn, this tensor, is called a stiffness tensor. It contains all the elastic moduli allowed by the spatial and other symmetries of the problem. And typically, under the assumption that your system is conservative, you can write down a stress, which in the language of continuum mechanics gives you information about the forces by taking a variation of the energy with respect to the strain. Pretty much like in Hooke's law, you can write the force equal the gradient of a potential. And then you can express the stress in linear elastic theory as a linear combination of the strain. When you do that, when you set up the problem to be a conservative form of elasticity, as it is ordinarily done, then this stiffness tensor K must satisfy an important property. It must be symmetric. Symmetric under the exchange of the pair of indices indicated in the equation that I'm pointing to. So when you flip Ij with Mn, as I did, this object is unchanged. The symmetry is the signature that your theory respects conservation of energy. So what we started saying is that, well, look, that may very well be true if your building blocks are passive springs, but if you're trying to make a generic theory of an assemble of a tissue, for example, composed of many cells that have internal source of chemical energy, there's absolutely no reason why this assumption should be made. We have to, if you like, remove this constraint. And so what we said is that we're still going to work with linear elasticity, so this relationship here between stress and strain, but we're going to give up the notion that an energy exists, and we'll give up the notion that the stress comes from a variation of an energy. And all you have to do, if you want to do that, is that you no longer assume that this K is symmetric. It's now composed of an even or symmetric part plus an odd or perfectly antisymmetric part described by this relationship. And this tensor will contain new elastic moduli that do not exist in systems that are conservatives. These moduli, you don't read them in Landau-Lifshitz because they would be forbidden if the structure was at equilibrium. But they determine how these things move, how they deform. And in particular, and this is really a very quick summary, if you do two-dimensional elasticity and you write down all the type of strains that you have, and we do here in a rather pictorial language, and all the stresses that you have, along with the bulk and the shear modulus that exist in textbook on two-dimensional isotropic elasticity, you also find this additional moduli called K0 and A. The reason why these moduli are normally not even mentioned is because if you take your system along a loop of strain deformation, the work done at the continuum level will be given by the area in the strain space times this odd moduli. So if you want to eliminate that activity, then those K0 and A must be equal to 0. Otherwise, these are the moduli that naturally arise, and they are the only one allowed by isotropy in two dimensions. So we can fully classify the response at the linear level between deformation, the strain, and stresses using symmetries, conservation laws, but removing only one of the conservation laws that we don't want, which is conservation of energy. There is no reason to exist in an active system. Okay, so this is all about how. Let me also mention that there's an inherent notion of non-reciprocity also at the continuum level, because, for example, notice that these off-diagonal entries are different. What that means is that if I apply, for example, a compression, I will generate torques via this coefficient. But if I apply a rotation, since this is a 0, I do not cause any pressure. That means that coupling different deformations doesn't undo the operation of the other. And this is the fact that the off-diagonal term in this matrix are not equal is the signature at the mathematical level of this odd moduli. And the reason why the response in two dimension is also chiral. Okay. There's one thing that I forgot to say when I started. You know, I cannot, of course, see as many people as I would if I were there in person. So if you want to interact with questions, please do so. It's better to answer a few extra questions rather than cover much more of what I want to do. So feel free to just storm in if the organizers don't mind. Okay. Now, what I've done up to now is to talk about linear response. But I want to convince you that this is by no means the rule. In fact, this system with internal feedback do not want to stay in the linear regime, not even the robots that we try to design to have that property. And let me show you why. So if we return to our building block, this innocuous linkage with motors, and you just write down some equation of motion, assume an inertial dynamics, but with this peculiar, just 2x2 matrix with the antisymmetric entry, what you will notice by diagonalizing that matrix is that these antisymmetric entries are responsible for introducing an imaginary part in the square of the eigenfrequencies. Okay, so they lead to explosion, unbound growth, as well as decay. So why is that? Well, I already said that they're responsible for the fact that if you take it around the loop, you inject energy. But if you do that indefinitely, this loop will become larger and larger because you keep injecting energy in the system. So all I'm saying is that this is an excitable medium. An excitable medium get excited. They get excited until some other mechanism doesn't stop that. Okay? And so to make that very clear, energy injection at the microscopic level must be balanced by something else, a nonlinear response, steric interaction. When that happens, though, you can have cycles, more precisely limit cycles. What you're seeing here is a loop made of those simple building blocks. I can replay it. And I'm plotting it in the space of shear transformation of these things, of this shape. And notice that it goes around and around and around. It doesn't stop, okay? Why? Because it's harnessing the microscopic energy being constantly introduced in the system, and the energy injection is stabilized by nonlinearity and friction and other imperfection of the system. So the bottom line here is that limit cycle turn this odd elastic material in something that can go into loops. And these loops, since they are associated with the ability of generating work, you may wonder, can we actually use it to do something useful? Can we actually take this active media and turn them into building block or robots or robotic things that can perform a function? So here what you see from the work of our collaborator, we've just taken the same, sorry, I apologize for the cheeky title, but I couldn't resist. You know, the wheel of that I'm used to in my car. Actually, I don't have a car, but I do have an electric bike. And so the wheel is essentially a rigid object connected to a shaft, and the shaft is connected to a motor. Now here you're going to see a different wheel, a wheel that moves autonomously by virtue of its own deformation. Okay, so what the wheel will do is what all wheels do. It will climb. Well, it will move. But notice that this wheel is climbing uphill. Why? Because it undergoes a cycle of deformation. That cycle of deformation creates work, and that work can be invested in overcoming some energy barrier to performing a function. And all of this, of course, happens deep in a nonlinear regime. And it's all enabled by the simple fact that at the microscopic level, this most stupid system has a minus sign here and not a plus. That's the only difference between two coupled pendulum in these systems. This asymmetry in the force, in the torque versus displacement law.
So can I ask, is the energy coming from the batteries that create the asymmetry? You're going to tell me this.
Absolutely. So hidden in each of these nodes, there is a battery. And that battery will absorb energy if the cycle goes counterclockwise or whatever, and release it if it goes clockwise. Okay. And the continuum theory will have the same property because you planted it in the building blocks, which you've done. And I would like to say before moving forward that such things exist in nature also. Like, for example, you could have systems that interact with forces that are non-central, but have a transverse component. For example, if you have things spinning in water, you have things called lubrication forces that are transverse to the direction of compression. And there are many recent experiments, including biological system of spinning embryos in the factory lab at MIT, spinning colloids in the lab of William Irwin here, or Steve Granick, that have investigated precisely systems that have that type of characteristic. And really, it's not hard to imagine if you put particles in a medium, in a fluid, the interaction between those particles do not have to come from a gradient of a potential. I mean, once you realize that, it almost seems very natural that these things should be rather ubiquitous in the world of soft condensed matter physics, at the very least. Okay. Now, let me make a rapid transition from discussing the mechanical response or the response function characterizing the system that have this asymmetric structure to discussing phase transition or non-reciprocal phase transition. This is a work done in collaboration with my colleague, Peter Littlewood, and two very talented postdocs, Michel Fouchard and Rio Anai. And actually, this work started very much with conversation. And I think it's fair to say that probably Michel and I were, more studying things like active matter, and Rio and Peter were very interested, among other things, into driven and dissipative quantum condensates. And some of the mathematics, I think, that you'll see, while I'll give you a more classical perspective on it, really straddles these two domains. And it's been really quite a fun collaboration for that reason, among others. So first of all, let's try to revisit, in the same way as we revisited the basic mechanical interaction, like a spring or a pendulum. Let's try to revisit for a moment, how do people think often, at least this is how I teach most of the time, maybe I should do some modification in the light of what we've been doing recently, how I teach phase transition. I usually teach it, and it works pretty well when you try to describe equilibrium phase transition at the very least, and even some non-equilibrium one. You usually think of an energy. An energy landscape, for example, here is a simple well potential, or a Davable well potential. And the phase transition is essentially a change in shape of this potential energy landscape, okay? And the rule of the game is that you try to minimize the free energy. The most stable phase wins, and the most stable phase is defined by the one that sits at the bottom of whatever potential you're driving. And even the dynamics, whenever you worry about it, like I did here in this equation here, it's a dynamics that comes from viewing your system as rolling, as a ball rolling down the potential energy landscape. Okay. Now, for the reason that I was trying to elucidate before, non-reciprocal interaction do not necessarily fit in that paradigm, partly because there is this inherent injection of energy that is associated with the asymmetric nature of these force laws if you do mechanics. And I would like to give you a concrete example of that. I'm going to present for you, or revisit for you, the XY model. Okay, and then I'm going to show you what the XY model looks like and why this connection with energy optimization is so important to my eyes. So what is the XY model? You might have encountered in a class of statistical mechanics, assuming that you have a lattice, and on this lattice you deposit these red arrows. Okay, these red arrows are spins. They can rotate in any direction. You can label them by this angle theta. At the position of the spin I, the angle will be theta I. Okay, and in the XY model, you want all the spins to take the same direction, to align with each other. Okay, if you view it as a model of synchronization, you want to align the face of all the spins. And the way this is done is to introduce an Hamiltonian. This Hamiltonian has a Jij, which is a coupling between the spin at position I and the spin at position j, and then you multiply by the cosine of the difference between the two angles. And if this Jij is equal to Jji, so the two spins interact with each other in a mutual manner, and this object is greater than 0, then you minimize this energy by aligning all of them, okay? And you can also write down the dynamics for this spin, which comes from minimizing this energy. And you just take a derivative of this cosine, you get a sine, and you may have a little bit of noise if you want to do statistical problems. Now, this is if you like, a lightning fast summary of how to think about critical dynamics in the presence of conservative interactions, which now let me give you a counterexample to that. Now, I cannot do it with spins, but in the same cheeky spirit of what you've seen before, we bought for the modest cost of $100 each, 5 or 6 robots. And these guys are, can be programmed more easily than spins. I mean, maybe some people can program spins too, but we just, if you like here, bought these robots. These are coming 2 species, the blue one and the red one, okay? And what we programmed is that the way robot A interacts with robot B is the opposite of what robot B interacts with robot A. In other words, if the blue robot wants to align with the red one wants to anti-align with the blue one. Can you see we have built in, at the level of the interaction, an inherent frustration, okay? Now you may say, well, why is that bad news? Why is that such a big deal? Why do I have to give up this H? Why can't I just use the same formula? I just assume that this Jij between the robot, the A robot and the B robot is antisymmetric. Well, notice this formula here. If the Jij is antisymmetric, well, look, the cos theta j minus theta I is symmetric. So if you take a product of an antisymmetric object times a symmetric one in these indices and you sum over them, that's going to be 0. That means that whatever behavior the spins are going to exhibit is not going to come from minimizing an energy, because this energy is identically 0 if you divide it as a quadratic form. Now, there could still be, notice, a dynamical equation that is well defined, exactly as before, but now in that dynamical equation, Jij is no longer constrained to be symmetric, okay? You allow for non-mutuality in the interaction of the spin I and the spin j, okay? And now you can see, well, look, assuming since you bought these 20 robots, instead of doing on a computer, you can lay down on a table and see what they want to do. How do they solve this non-reciprocity, or this frustration that exists at the microscopic level? So one thing I would like to do before playing this movie is to tell you that no external torque is applied to each robot. A single robot in isolation will never be able to rotate. However, when we program them to have this non-reciprocal interaction, such that, let me repeat, A wants to align with B, but B wants to align with A, represented by this, what you see is the following. And please let me know if you see the movie. What you should be seeing, even given our pathetic experimental abilities, is that the species of the blue robots are rotating counterclockwise, and so do the red one. They tend to have an angle with respect to each other. And there's no way that these guys are going to all align in one direction. There's no static solution of an equilibrium problem. If you want to view the average orientation of the red ones as an order parameter, a vector field, and the one of the blue one as a blue arrow, these order parameters will continuously cycle. This is what I would call a time-dependent phase. And I stress, this is not coming because each robot has a single torque on it. It's coming because of the frustrating interaction that these robots are experiencing. Okay, so when you imagine having, which is too expensive for my pocket, building this with a billion of such agents, and you build a continuum description of this will be a time-dependent phase. And the transition to this state will require a special language to be described that is not the one of energy minimization. Okay, I like to.
Can I ask a question? This is so amazing. So can you explain a little bit why, like, the species of the same kind would be aligned roughly all the way to the same direction?
Oh, because we programmed it. We programmed the one that are of the same type, the blue ones, to align with each other, and the red to align with each other. But the red and the blue have this asymmetric interaction. Think about it as the cross term in that matrix, as we showed in the mechanical problems that have the peculiarity. We could have done something else too, if you like.
I see. Thanks.
Okay. But the rotation comes purely from this asymmetry. Okay. Now let me give you another example. I want to introduce you to something that people usually consider paradigm on an equilibrium phase transition, the flocking model. But which is, a simple model, Toner 2 equation or Vixen model. It's a simple model of flocking. It's a model that treats birds as flying spins. I don't know how the birds feel about that, but let me describe it to you. So imagine that you have a little spin here in blue, and this bird looks around in a certain regional space denoted by radius, and checks out the orientation of all the other birds around. He takes an average of those orientation, and then he adds some noise to it, and that will tell the new direction in which that bird at that position will move in space. This is called the Vixen model. And you can develop coarse-grained theory of this Vixen model called Toner 2 hydrodynamics. Okay? And this model, depending on the relative ratio between the intensity of the noise and the tendency of these birds or spins to align, will exhibit two phases. A very high value of the noise, there will be a disordered phase in which all this little creature represented by very small dots in this movie will move in random direction. And if I plot the average velocity, it will average to 0. Or there will be a phase in which they all align and they move in a single direction, which is spontaneously chosen. It's a spontaneously broken symmetry. And the average velocity field is fixed in space. Please notice the birds are moving, but the velocity field at the coarse-grained level is just one orientation, which is fixed in time. This type of transition, despite having many non-equilibrium features, can still be described in terms of an optimization principle, because the order parameters essentially are frozen. Okay, so you can still describe a polarization of a velocity field, and the transition can be described as a change in the shape of an energy function, or the generalization of an energy function. Now I would like to provoke you.
The generalization of energy function, if energy is not conserved, how do we build some kind of a functional?
Yeah, so you don't do it. I mean, it's not. I mean, what you do is you build a Landau theory, and you construct an object from which generalized forces can be constructed, and the dynamics is inherited from that. So it's not correct to call it an energy functional, but it's an object whose optimization leads to the dynamics.
Like dissipative function in mechanics, when you want to include the...
Well, the hydrodynamic equation also have dissipative terms, but there is one which looks like, if you like, a generalized elasticity, which is described by that bit. You know, a Landau theory, quite plus dissipative terms. To show you the difference between the ordinary Vixen model and the modification you would have to do to address the problems I'm interested here, I would like you to consider a Vixen model, let's just say this model of flying spin, composed of two types of spins, one the blue one and one the red one. And we're going to assume first that the blue and the red interact with each other in the same way. So this interaction parameter Jij is symmetric and greater than 0. Then even if you have two species, the net result will still be that both species, the red and the blue, will move in the same direction. Okay. Notice that the two order parameters, which are the velocity field for the two species, are both oriented in a fixed directions, and they're also aligned, because this is essentially a model of ferromagnetism. Okay. If this J was negative, that would be going in opposite direction. Now, what I want, and these are the equation of motion that this system will have to satisfy. Now, what I want to do is I want to allow the possibility that Jij is not symmetric. So it will contain both a symmetric component and an antisymmetric one, as represented in the schematic equation that I wrote here. And I want to ask, what happens to these birds now? And one of the new phases that you can observe is the following. Notice here that these two types of birds are rotating constantly. So if I now draw the velocity field as before, and I plot it on average for all this system, both the red and the blue vectors shown here will constantly rotate in time. And with the chirality of the rotation, which is spontaneously broken. They could have gone clockwise, they could have gone counterclockwise. Okay? Now, this is what I would like to call a time-dependent phase, as opposed to the previous one. Okay? So depending on the symmetry or antisymmetry and sign of these exchange interactions, we'll have different behaviors that are summarized in this slide. If the interaction, first of all, if the noise is high, it's just disordered. The velocity fields are just on average 0. If you have them being symmetric and greater than 0, you have flocking, which means ferromagnetism in this flying spin. If they're symmetric, but is a negative number, there's antiferromagnetism or anti-flocking in this picture. But what we're really interested is this chiral phase at the end. Why? Because when looked in the space of the order parameter, which is at the bottom of the slides, that is the only one in which the order parameters themselves are rotating. And these are the time-dependent phases that we're particularly interested in. Okay? Now, how do we describe all of this? Well, I'm going to give a sort of like maybe simplified view of it in the mean field, at the mean field level. So remember that there is this JB and this JBA coupling. So we can construct a very simple phase diagram. We can calculate it, construct it numerically and analytically. And we put on the y-axis, on the x-axis, the following quantities. On the x-axis, we have the symmetry of with the how to say, JAB plus JBA. Okay? And on the y-axis, we have JAB minus JBA. Now, let me just get you some because all these A and B's one after the other is very confusing sometimes. Let's assume that this interaction were symmetric. Then JAB is equal to JBA. So you will be living on this axis, okay? And of course, the sum of these two things would be a number that can be either negative or positive. If it's positive, you align, as you saw in the previous slide. If it's negative, you anti-align, okay? And that's the transition between a ferromagnet and an antiferromagnet. What's interesting for us is, what if JB minus JBA is not zero? Because that means that there is an asymmetric coupling. And what you can see here, that in the middle, when you try to go from the anti-alignment to the alignment, there is this chiral phase, the time-dependent one that we're interested in. So if you have a finite amount of non-reciprocity, you will be marching on this dashed line that I'm indicating, okay? And one of the things that I want to understand is that how do you draw this red line that separates a time-independent phase, like the aligned one, with this, from this time-dependent one, like the chiral that I showed you? What happens on this point, or what happens on this red line? How do you draw it? So that's the rule of the game. Let me remind you that if I plot the same thing here on the axis, on the x-axis, I call it J plus. Before and now, what I'm showing you is just a cut corresponding to this dashed line. Then this point, where I go from anti-alignment to chiral, is this point here in red. And there's another one on the opposite side. So what's going on is that in this area, in the chiral phase, the order parameters make an angle with respect to each other that depends on where you sit on this line. Okay, it will become, the angle will become 0 when you cross in the aligned phase, or it will become 180 degrees when you go from the chiral to the anti-aligned. But the important point is that when you are in the chiral phase, these vectors are moving. Whereas when you are in the anti-aligned phase or in the aligned phase, the vector order parameters are static. So we have to describe this transition between static and dynamic behavior that happens at this point, okay? So how do we do that? Well, generically, our system is represented not by an energy functional, but it's a dynamical system, a spatially extended dynamical system that I wrote schematically as a bunch of equations for a bunch of fields, nonlinear equations for a bunch of fields labeled by my index A. So in order to identify this point, what we need to do is we have to calculate the Jacobian of this transformation. And what we discover is that at this point, at this red point, the Jacobian of this transformation, the matrix, if you like, if you write it as a simple 2x2 matrix, which typically it isn't, it's a higher dimensional matrix, becomes defective. What does defective mean? It means that this matrix takes up a Jordan form. It can no longer be diagonalized. Or if you prefer, the eigenvectors of this matrix at this point, at this red point, are coalescing. Two of the eigenvectors are coalescing. Such a thing is called in linear algebra an exceptional point. Not everybody is familiar with this name, but it's a simple concept of linear algebra. I would like to stress one important aspect here. Crucial to all the story is that this f of A cannot be expressed as the gradient with the label A of a potential. Because if you could, then this object, LA of B, would be symmetric under exchange of A and B. Okay? But our dynamical system do not have that restrictive property. Now, there's a very rich literature in quantum mechanical system going back to Bender and Butcher collaborators, as well as Atano and Nelson, which deals with similar problem in quantum mechanical context, sometime under the label of non-Hermitian quantum mechanics. But I prefer to introduce the idea of exceptional point with a more mundane physical example. Let's consider for a moment a damped harmonic oscillator, okay? Now, a damped harmonic oscillator, you can write down a second order differential equation. Many of you will have seen this equation as damping, as a restoring coefficient. If you write down this differential equation as a 2x2 matrix, by doubling the number of variables, you write one for momentum and one for displacement, then critical damping, which is the value in parameter space, where you go from exponential decay and no oscillation, which is the overdamped regime, to starting seeing some oscillations because you now have a complex eigenvalue, well, that is an exceptional point that exists in that matrix, as you can see from the structure of this matrix. So if you like, a simple reason or a simple manifestation of this exceptional point, you already know about it in the damped harmonic oscillator. Now, the question in this problem is to understand what are the two eigenmodes of this matrix that are coalescing. What is their physical interpretation? And I think it's better seen on the next slide. So this is the exceptional point. And I want to convince you that the two modes that are responsible for this coalescence are, one, the Goldstone mode, which correspond to the bottom of this Mexican hat potential, which stems from the rotational invariance of this system. And the other one, if you like, the massive mode, if you want to use that language, or damped mode. And so what happens as you approach the exceptional point in parameter space, you're going to see it in this movie, is that these two modes coalesce. And right at the exceptional point, there isn't more an appeal mode. Both of them are coalesced at the bottom of this potential. In reality, it's not even a good idea to talk about the bottom of potential. Why? Because while in equilibrium phases, you can draw this potential and say that the dynamics is just rolling down the potential. What happens in this non-reciprocal phase transition is that, if you like, there are additional transverse or non-conservative forces, such that when your system tries to roll down the potential, it's also moved in directions in this potential energy landscape that cannot be described by gradients of that potential energy. And in fact, once you start seeing the cyclic motion that we call the chiral phase, what's happening is that you're constantly rolling at the bottom of that potential, and that cyclic motion, by definition, cannot be described as an optimization problem. Okay. I would like to make another couple of technical remarks. The chiral phase that you saw, in which you restore the continuous symmetry, you have a dynamical restoration, if you like, or your spontaneously broken rotational symmetry, is only one example of the dynamical steady state that these order parameters can have. For example, one thing that you can do in our system, and you can study, you can discover by tracing the phase diagram other states or other phases. For example, you can restore dynamically a discrete symmetry, like a Z2 symmetry. And then you have this swap phase in which literally, instead of rotating, the blue and the red arrow are swapping with each other. Or you can have a chiral swap phase in which both of these motions are happening. The bottom line that I want to draw with these slides is that there's a whole zoo of these phases, but they're all characterized by the fact that to describe them, you need a movie of the order parameter, not just a static snapshot of it, because they are necessarily time-dependent phases. They restore some spontaneously broken symmetry. I would also like to say that things become significantly more complicated when you go beyond mean field. And one way to do it is to assume that your system is not homogeneous. Then what can happen, for example, in these models that have flow, hydrodynamic flow, like the self-propulsion that exists in the flocking model, is that the phase boundaries that you calculate at the level of, at the mean field level, assuming in a uniform system, turn unstable. And there are pattern formation triggered by non-reciprocity. In particular, when you do that, if you write down the equation for your order parameter, not only you have the so-called exceptional point, but you have to have also gradient terms responsible for the variation of this order parameter. And one thing you can see is that even when you predict at the mean field level there will be alignment, in reality, the system will nucleate topological defects in the velocity fields, which are vortices and anti-vortices. And this type of non-equilibrium defect unbinding transition, where defects are constantly, vortices and constantly unbind, are not described by classic Castells-Thales theory that you used for an equilibrium XI model. So there's a very rich mathematical arena backed up also by experimental observations. So let me try to build up a little bit of a schematics here. So how do we attack in general these problems? Well, I mean, you know, in a sense, I mean, you will recycle a lot of the standard approach based on symmetries and conservation laws. The only thing is that you do not want to start with an energy function. You don't want to start with an Hamiltonian or an action. What you do is you study the system you have, and you pick up an order parameter, say in the cases I showed you was a vector order parameter. There is some symmetry that is appropriate to the problem at hand. And then what you will do is you will build what I would call a non-reciprocal hydrodynamics, or a node hydrodynamics. What that means is that you write down the dynamical equations. So you write down the equation for your field, and notice that there will be generically a multitude of fields. This vector is a subscript A, so A can be the red, the blue, whatever many fields you want, but at least two, because you can only talk about non-reciprocity if you at least have two. And you write down all the terms that are compatible with your symmetries. But the important thing you want to remember is that when you write the matrix or matrices or coefficients that couple your fields, you do not want to exclude antisymmetric terms. Whereas if you started with an energy functional and you impose the same symmetries, then these asymmetric terms will be excluded to start with. Okay? And so, especially when dealing with physical problems where you're very tempted to use an energy thing, you will be missing things that can happen. Okay? From the perspective of a dynamical system, what this is a well-known thing is called, you know, you're writing down the equation for an equivariant dynamical system subject to certain symmetry. And this is a good book for if there are graduate students in the audience interested in learning more. And in all of the things I'm going to be I've talked about with flocking, synchronization, and also pattern formation that I'm going to talk now, you always have essentially the same equation plus gradient term. The only thing that changes is the interpretation of this velocity field. It could be this vector field. It could be the velocity of self-propelled particle. It could be the average phase of coupled oscillators, or it could be also the amplitude at position of periodic patterns. And the physical meaning of that rotational symmetry can also change. Let me give you an example in pattern formation. This is like one of the workhorse of pattern formation. It's called the Swift-Hornberg model. And I say standard because I'm going to do the non-reciprocal in a moment. So this is essentially a field called U. And please notice that this is a nonlinear differential equation. There's the cubic term here. It's also spatially extended. There are gradient terms. Now, in the ordinary Swift-Hornberg model, depending on the value of this parameter R, in the presence of a single scalar field, if R is less than 1, there are no patterns. If R is greater than 1, you can see sinusoidal pattern forming. Now, and notice in this case, the symmetry is translational symmetry. Now, what we're going to consider, it's a slight generalization. We have two species of field, UA and UB. And these two fields are coupled by a matrix of coefficients that I'm calling RAB. And guess what? I want this matrix to be to have a non-symmetric component, or if you like, an antisymmetric component that couples the field A and the field B asymmetrically. When that happens, you will have patterns that are moving. You see, these two patterns that are moving in the Z direction, they're a little bit like the two vectors that were rotating. It's just that in that model, the symmetry in question was rotational. Here is translational. But this problem can be analyzed using the same language. The Goldstone mode has a slightly different meaning, but the place in phase space, when you start seeing these traveling waves forming an angle with respect to each other, is an exceptional point in the same sense that I described below. And in fact, this problem, like many problems of pattern formation, can be treated using amplitude equations. An amplitude equation is written here. You know, you have an amplitude, and in this amplitude equation, the field that denotes the amplitude can be coupled asymmetrically. Whenever that happens, this mechanism of phase transition that I've been describing at length, that cannot generically be formulated in terms of energy minimization, unlike the reciprocal Swift-Hornberg model, must be considered. And there are many examples in nature, from overflowing fountains that display chiral motion at edges and other interesting systems, including ones that we digged up in the literature and revisited in the light of these considerations that follow what I've been describing here. There's another connection that, in the spirit of broadening a little bit the description here, I would like to stress. In the first slide, I also mentioned system with gain and loss. Many people in your faculty studied this thing. For example, Doug Stone, with whom I collaborated, also in a Simon investigation. But typically in those contexts, especially quantum one, when you have gain and loss, the typical setup, and I'm oversimplifying a little bit by writing down a 2x2 matrix as usual, is that you do have an Hamiltonian. But you have an Hamiltonian which has complex, let's say that I write the diagonal part of this Hamiltonian as complex entries. The red one corresponds to gain, because you can imagine it will lead to exponential amplification, a bit like the toy that I showed you at the beginning, or loss, the one with the minus sign in front. This story was all about a different matrix, if you like, an antisymmetric matrix that has zeros along the diagonal and opposite entries on the off diagonal. So this is what we've been calling non-reciprocity, and it's this object that when you sandwich in a quadratic form cannot be represented by a quadratic Hamiltonian. However, notice that if you take this matrix, this prototypical Hamiltonian with gain and loss, and you apply a unitary transformation or a change of basis, you go from this object to precisely this one. So there is an inherent connection between system with gain and loss treated in optics, mechanics, quantum mechanics, and the non-reciprocal system of the type that I described. One thing that I do not have time to discuss a lot is the study of critical phenomena in this context, but I've listed down here a few papers that do something in this direction, but they're not representative, and they're a little bit biased by my own work and the one of my collaborators. So let me try to draw some conclusions. I described for you a mechanism of transition, of phase transition, that, if you like, is mediated by this exceptional point. Cannot be described purely in terms of the geometry of an order of an energy landscape that changes as a function of a parameter. This idea is applied to many problems: synchronization, flocking, pattern formations, but also other work here that I list, the phase separations. And it seems that the same mechanism is at play in all of these different domains. Sometimes the critical dynamics can fall in what is called Model A or Model B critical dynamics, but they all have in common this ubiquitous presence of exceptional points as the mediator of the transition. And with that, let me say that our paper has a visual summary that hopefully can serve as a guide for those who want to build their own exceptional phase transitions. And thank you very much for your attention.
So let's see, if people have questions, maybe the best thing to do is to either just shout them out or type them in. I have one to start. I wonder if you could say a little bit about the critical phenomena of these and whether, I guess, whether exceptional points, should I think of those as being, having extended critical fluctuation?
No, absolutely, absolutely. I mean, this is a general feature wherever you study. I mean, this exceptional point essentially share many similarities. In fact, they're very similar, the things I'm talking about, in what is called Bogdanov-Takens bifurcations in the context of dynamical system. And the notion that fluctuations are amplified near bifurcation is, of course, a common one. So what's happening, the reason why this is particularly interesting, and let me try to see whether I can provide a little bit of an intuitive explanation, is that at the exceptional point, as I showed in this movie, the massive mode and the Goldstone mode coalesce. Okay, now that coalescence means that if you imagine taking that hypothetical ball and knocking with some noise, the the motion of that ball will always be projected on the manifold of zero resistance. So there will be an inherent amplification of noise due to this feature. And I would like to stress that this is not a phenomena due to the interaction terms in your, like if you do write the dynamical equation, there's something screwed up in the linear term. Notice that when I was writing things down, let me try to use a language that is more technical than screwed up, but where am I? Let me go to that non-reciprocal hydrodynamics.
Towards the end of the talk.
Yes, here. Notice that when I'm talking about this A-B term, this is the linear term in the dynamical equation. That means that this term would be the quadratic term if you could write an energy. So already at the level, if you like, of the linear coupling, there's something problematic. And of course, when you then go to the phase transition level, you will see that this immediately appears, even in, how to say, a quadratic treatment of the problem, or linear treatment of the problem. So
I appreciate that it's different from, actually the same question, but I didn't get the answer. So, I mean, usually there is a notion of critical exponents. And of course, there is no thermodynamics, but I can look at linear response. I can add some small force and look at the reaction to this force.
Yeah, yeah.
And it probably will be non-local. And perhaps, I don't know, maybe there are some correlation lengths, a correlation radius, which diverges. I just,
yeah.
Notions of the conventional theory would be transferable to this one? Or
well, the attempt that we've done so far has shown three things, essentially going through all the points you made. You said you apply a force, you apply perturbation, you do linear response. So first thing, the way you apply the perturbation leads to a response that is, if you like, in the wrong direction.
Sure. Yes,
you
but still
apply
linear.
A longitudinal, or even in the internal space of the order prime. You apply longitudinal one, you take a transverse response.
Yeah. There is no angle, I understand.
Good. So then you can look at the correlator between these two fields. So the first thing I wanted to say is that before even discussing correction to the critical exponent that already exists in the theory without non-reciprocity, there will be new correlation functions that would have been zero. Even at the quadratic level. Okay. Now, when you calculate the critical exponent for this new correlation function, well, there's no equilibrium counterpart, and you can calculate them, for example, using Martin-Sijar-Rose technique or Keldysh. And the other one that existed before, they're strongly renormalized, and the fluctuations are very intense.
Okay.
So it's not that it's a mystery that we cannot do it, but the effect is very strongly pronounced. And there are even new, there's not only strong correction to the existing critical exponent, there are new ones you have to define because the responses are non-trivial, precisely as you indicated. Any other question? Yeah, and some of those papers that I cited at the end attempt to do that.
Okay, yeah, I'll look at it.
So. Sorry, if I can add one thing. A fancy term that sometimes people use is PT symmetry breaking transitions. And one of the early examples of a field theory with this characteristic was done by Bender and Messina. And some of the papers, including my own that I cite, are, if you like, follow-ups.
Thanks.
So you gave the example of how the wheel extract the, how the wheel climbs uphill by extracting the energy from the motor. Would it be possible for the wheel to extract energy from the environment when, for example, it's going downhill, like it stores energy in the wheel?
Yeah, so I'll try to answer the question. Please tell me if I don't. I had a little bit of trouble hearing you. There was a bit of disturbance on my end. But if I understand correctly, in the early part of the talk, I put we put by hand some motors inside those little mechanical systems. But in general, what you will have is a coupling of a system that I call the system to an environment. And the energy will be leaked through a non-trivial coupling to the environment. And I think this is exactly what people call active matter. It's an effective field theory in which you if you like, ignore some degrees of freedom that can pump energy in your system and leak, and energy can be leaked into them. And then you look at the system, and of course the system will be out of equilibrium, and it could display unusual responses, unusual phase transition, because in a sense you decided not to look at all the degrees of freedom. If you did look at all the degrees of freedom, you would find precisely a well-defined physical system that does not display all these exotic things.
Just a quick follow-up. Would it be possible to draw energy from the environment into the system?
Yeah, absolutely. This is, for example, look, the example that I was giving of the particles that are in a fluid, they are spinning, and when they move, they have these forces that are non-conservative. Well, the energy there is coming both from the field that makes them spin continuously and from the fluid.
Okay, that makes sense.
You see what I'm saying? Yeah. So in a sense, it depends what you call the environment. The environment is everything that you don't call the system. So the battery is in the mechanical system. We're the environment.
I have a question. So what is the matrix that becomes defective?
Is the
dynamical matrix? Or what?
Is the
or is it the linear thing in the equation?
Edward, so what you have to do is you have to, if you like, linearize your nonlinear dynamical system around the point in phase space where you are doing your analysis. For example, say that you come from the aligned space, you will linearize the equations for the fluctuation in the order parameter around these parameters. And
so it's not the bare linear term, it's some, it's some display.
Absolutely, absolutely.
Okay.
It's the linearization of this dynamical system that will typically be nonlinear. Like you saw, for example, the bare theory in the case, for example, of, well, even here you can see that there are cubic terms. And in the case of Swift-Hornberg is this beast here. And the G is absolutely essential. That number will enter the L operator that is the Jacobian. Yeah, absolutely. This is crucial, actually. Otherwise, you would not be able to talk about phase transitions if you did not explicitly incorporate those nonlinear terms.
Okay, yeah.
So it's beyond band theory of the phonons that exist on an homogeneous ground state.
So why is there such a limited number of behaviors? Just alignment and then chirality and not, but as soon as you have inhomogeneity, then you have...
Oh, well, actually, first of all, once you have inhomogeneity, there's a whole host of complications. But even when you have only even in the, say, flocking, when you have the two vector order parameter, at the beginning, I only showed you 4. Disorder, ferromagnetism, antiferromagnetism, and chiral. But then in this slide, I said, well, look, if you study the phase diagram carefully, you now have, for example, also the swap phases. I don't know if you can see whether you swap the blue with the red. Okay, all these chiral swap phases here, where they rotate like the chiral, but they also swap. So,
but is there a whole huge part of phase space where it's really chaotic and there's no
absolutely
order?
Absolutely. In fact, as I was saying, here, for example, we draw this phase boundary, describing as in mean field as a transition between 2 well-defined phases. But in some theories, where there are exceptional points at background flow, we can actually show that the presence of the exceptional point at broken Galilean invariance triggers pattern formation or chaos, if you like. So that can also happen. But the general wisdom, the way I like to think about all this zoo of phases is the following. Your system has some spontaneously broken symmetries. And then you can dynamically restore them. The chiral phase dynamically restore a continuous
that's really interesting.
That's the life.
We don't like the broken symmetry. We're going to actually dynamically restore it.
Exactly.
I think that's fascinating.
And of course, how many you have depends on how complex your dynamical system is and your order parameter.
We have one more question from Charles, who's here.
Hi. I was just wondering, I think you mentioned something about locality as well, but I put my question in the chat too. But when you have something like bird species, it seems like they should couple strongly to maybe in like a peripheral line of sight or look spatially closer to each other, or these car motors, you might imagine that some have a faster response than other because there's better motors or have less battery, however you engineer that into system. So what, how have you explored that in these systems, and not just getting maybe global chiral responses, but local domains of these responses?
Yeah, so this is something that I haven't done a lot of, but one thing you can do, people have studied, but I don't think that they've done this type of analysis for it. You know, in my discussion of the flocking, I said, let's have two birds, I don't know, that the red and the blue, that interact with each other in non-reciprocal ways. But as you pointed out, it's enough to give the birds a cone of view. I don't know if you can see my hands. If I'm a bird and I have this cone of views, I'll see the ones ahead of me, but the ones ahead of me don't see me. So even with a single chemical species, there is at the level of the microscopic interaction an element of non-reciprocity being built in. Now, in order to trigger all the song and dance that I've been discussing today, what has to happen is that upon coarse graining, which is something that we did at great pain in the supplementary information of this paper, that microscopic non-reciprocity must survive in the hydrodynamic theory. And this is not always the case, because sometimes its effect does not produce this antisymmetric coefficient that I was discussing. If that is not the case, you will not find analog of this exotic phase. So it depends a little bit case by case, but it's worth exploring what you're saying.
Maybe we should thank Vincenzo one more time now.
Thank you very much. Thanks. Bye.
And this is a good time to break, but I think we are, actually, let me turn.
Shall I switch off this and go to the other place where I'm supposed to meet you?